Okay, so what we want to look at is a way to collectively, you know, visualize the several of the questions that we already solved in the same framework. So this, this particular way of looking at several counting problems in the same framework was done by, or at least to us, that is what is known, is introduced by Giancarlo Rota, so who was the advisor of Stanley, and in his work, Stanley has written about this in detail, and we are going to just look at that. Okay, so what we have is the following setting. We have a set B of balls. Okay, and then you have a set U of urns or bins or boxes. Okay, so you have a set of boxes and you have a set of balls. Now what you want to do is to distribute the balls to boxes, right? You want to distribute all the balls to boxes or place the balls into the urns, and then count the number of ways to do it. Okay, so that is all we are going to do, right? So we are going to take the boxes and then balls and put each ball into some of the boxes. Okay, so all the balls you want to take and then distribute to boxes, and then we can say, like, there are some restrictions that we want to look. This is the general setting. So what are the possible things that you can do in this, right? What kind of restrictions you can do? So let us look at these restrictions one by one. So one of the things that you can think is that, let us say, if you if you if you have your boxes and then your balls, right? So you can say that, okay, there is no restriction at all. You will say that, okay, you put you have to just distribute the balls to boxes. You can do whatever you want, right? Whichever way you want, you can do it. Then you can also say that, okay, I don't want you to do anything like that. I want you to put at most one ball into a box. Okay, so a box cannot contain more than one ball. That is one restriction that you can put, right? Another restriction that you can put is that every box should have at least one ball, right? Say that, okay, every box must have at least one ball. In other case, you can say that every box must have at most one ball, right? Yeah. So this is the first case was the at least one ball. Then you will say that, okay, you can have 0, but you must not have more than one. So these are some kind of restrictions that you can put. Then what other restrictions that you can put? Other conditions that you can put. For example, you can say that, okay, I have labeled the boxes, right? The boxes are different now, right? So box 1, box 2, box 3, box 4, kind of boxes are labeled. Then I can ask the same question, right? With the labeled boxes, if the balls are going to the boxes, and how many different ways are there? If I allow at most one, at least one, or arbitrary. Then you can say that, okay, my balls are also colored, right? They are not just identical. They are not necessarily identical, right? So I will say that, okay, they are colored. So then if they are colored, then how many different ways I can do? Then you can say that, okay, the balls are colored, but the boxes are not labeled, right? They are identical. So if that is the case, Then what you can do, right? So if the boxes are not labeled and then the balls are labeled, then what you can. So these kind of different questions you can ask, and you can see that there are altogether 12 such possibilities. So let us list them. So one is that like each urn or box must have at least one ball in it. Second is that no urn can hold more than one ball inside, and there is no restriction on how many balls can go to a box or an urn. So then what we said is that okay. So the different cases that we can have is that the balls are labeled to make them distinct, and the urns are also distinct. So the both boxes and the balls are labeled. Then second case is that the balls are all identical, but the urns are labeled. And third case is that balls are labeled and urns are identical. Then balls are and urns both are unlabeled. That they are all all the balls are identical and all the boxes are also identical. So in this case, what you can see is that like for each of the four cases, you can ask the previous three situations, right? You can ask these questions. What happens if these are the restrictions? So there are 4 into 3, 12 possible ways. So this is called the 12-fold way. Now let us try to put it into a nice table, right? So you have the balls, the urns, right? Then the cases that are distinguishable or labeled, and indistinguishable or unlabeled, and then these are the 4 into 3 choices, right? Where the 3 choice, right? We can any number of available balls in a box is allowed. Then at most one per each box, and and at least one per each box, right? So and then you want to count out, you want to find out what are the entries in each of these boxes, right? This one, what is it? What is this? What is these are the 12 cells you need to fill, and that will give you the answer to the 12-fold way question. So what are these numbers? So I want you to stop this and then think about this and fill up the numbers yourself, because we have already solved all these questions. So each of these questions we have solved, at least enough material we have covered using which we can solve all these questions. So think about this and try to work out the entries, and then once you fix, once you fill all the entries, see whether they match with the observation that we are going to come up with. Okay. So we can also look at this question in terms of functions, as many of you might have already immediately noticed. So let us say that your sets are like n and k, finite sets, where cardinality of n is equal to n and cardinality of k is equal to small k, right? Now we want to count the number of functions, let's say f, that map from the set n to set k, where first case is that f is arbitrary, right? F can be any function. Then we say that okay, we insist that f must be an injective function. Then you say that f must be a surjective function. So these are 3 possible restrictions that you can put. And then similarly, we can say that okay, the elements of n or k may be identical, or they are labeled to make it distinct. Right? So these are the 4 different scenarios. So 4 into 3, 12 again. So what are the cases here? Right? Elements of n, elements of k. Right? They are distinguishable or indistinguishable. Right? Indistinguishable means that there is no label; they are all identical. Distinguishable means that they are labeled; they are all distinct. And then you can say that any function is allowed, or injective functions are only allowed, or surjective functions are only allowed. So these are the 12 ways, and these precisely correspond to the previous cases of balls and pins. So, there is no difference. This is just another way of looking at it. So we are going to count this, or find out this cells by looking in one of these cases, right? We will either look at as a function or as a balls and boxes question, and this will give you some, different kind of intuition. At least I hope so. So let us begin. The first case, right? So what is the first entry here that we want to fill, right? So that is that we have distinguishable elements, right? Distinct elements in n and labeled elements in k also. And then we want to say that any function. So if the function is any function, then obviously we have already done this. That is one of the first questions that we did. So this is the total number of functions. Any function is allowed. So how many functions are there from an n element set to a k element set, which is k raised to n, right? So because why? Because f of x for any element can be any of the k possible elements. So because any element can be mapped to any of the k elements. So each one has k choices. There are n elements, so k raised to n. Okay. And in the terminology of urns and balls, we have cardinality of u choices for the first ball to be placed, right? And cardinality of u choices for the second ball to be placed, because any possibility is allowed, right? You can put as many as you want in any of the urns, and so therefore the ball has that many choices, right? If you are going to put the first ball, you can say that okay, it can be any of the u. Second ball, again, it can be any of the u. Similarly, all the balls. So therefore, cardinality of u power cardinality of v choices are there, which is what we were doing. Okay, so the first entry we have filled, right, which is k raised to n. Now let us look at the next entry, right? Next entry means that, let's say, in the same row, the second entry. So which is the injective f. F must be injective. So then what can we say? So let us say that n is the set x1, x2, etc., xn. Then if you take the first element, right, f of x1 can be any of the k elements. But if you take x2, once you fix an image for x1, x2 cannot be that image, right? Because we want it to be injective. So therefore, f of x2 must be any of the remaining k minus 1 element. So similarly, you continue, you will get k into k minus 1 into etc. k minus n plus 1, which is the n permutation of the k elements, right? So that is npk, k pn. What was the notation that we use? Right, yeah. So yeah, so this is precisely what we want. Now when n is greater than k, we will see that this quantity is going to be 0, because you will have k minus k coming there. So therefore this will cancel out, and therefore it will be 0. So if n greater than k, that will be 0, but otherwise it will be this one. But we can just write it as within bracket k and outside k. Now let us also look at the third case, where you want the functions to be no, 1 second. What is that? Surjective. Okay. Now to count the surjective functions, let us assume that initially the elements of k or the urns are unlabeled. So we were looking at the labeled case, but let us look at the unlabeled case. Suppose they were unlabeled. Now if the boxes were unlabeled, then placing the labeled balls to k boxes is basically partitioning the the set, right, n, to k blocks. right? Because we are just saying that okay, they are on label, so which box contains what is not important, but each box how many elements or which elements are there, right? That is the only thing that makes a difference. So therefore it's basically partitioning the set n into exactly k blocks. So now that is if the boxes were unlabeled. Now if the boxes were labeled, then it also matters, right, which box this has gone to, right? So basically the order of the partitions are also important, which means that you can, once you have the order of the blocks are also important. So once you have the blocks, you can permute them in any way, right? So there are k blocks, so therefore k factorial ways to permute them. Therefore we have k factorial into s and k possibilities to do this, right? So where s and k we define to be the number of ways to partition an element set into k blocks. So we have filled up that entry, right? We can fill that entry now with the s and k into k factorial. And the fourth entry, which is the entry below this, is going to be the case where the balls are identical and the boxes are labeled, right? So the elements of n are identical, right? The balls are identical, and the elements of k, which corresponds to the boxes or urns, are distinguishable or labeled. Now in this case, what matters is that how many balls each urn gets, because the balls are all identical. So which ball goes where is not important, but only how many balls are going to each of the labeled urns, right? So therefore you can think of the urns as the variables which takes the values, right? Like which is the number of balls, right? So this is basically like u1 plus u2 plus etc uk, where ui is the number of balls that the ith urn gets, right? So therefore, and this must come to n because we are distributing n balls to the k urns, and we already know how to solve this, right? We have done this. That is the non-negative integer solutions to the equation, which is k plus n minus 1 choose n. So we have a solution for that. Now this is also the number of n element multisets that can be made from a k element set, right? Because instead of looking at as choosing the balls to be placed, you choose the urns, right? And then decide, okay, this ball must how many balls go to each of the urns, right? So this is basically choosing the urns, and that can be looked at as the number of ways of forming a multi-set from a k element, right? K element set is the set of urns, right? From this you are going to you want to select some copies of each of the urns, so that you get an n element multi-set, which is the total number of balls, right? So so therefore you can think of this as the number of ways of selecting an n element multi-set from a k element set, right? That is also k plus n minus 1 choose n. So we already saw this, both notions for this parameter, and this matches, right? Okay. So therefore we have filled up these many entries, right? So we have first 4 entries we have filled up, k raised to n for the arbitrary functions, and then k plus n minus 1 choose n, where the elements or the balls elements of n or the balls are unlabeled. Okay, fifth case, which means that we have injective f, right? So injective f means that you are saying that you have at most one. Now, so which means that each urn can get at most one ball, right? So we need to choose which n of the k urns can get the balls, right? So you are saying that you have to distribute the unlabeled balls, right, to distinguishing bins. So which means that each bin or urn, so each urn now can get at most one ball, right? So which means that you have to select which of these which of the n uh, which of the n urns are going to get the balls, right? Because each one can only get one, so therefore, and the balls are identical, so it doesn't matter. So you just choose an n element subset of the total number of k elements subset, which are the urns which are available, right? So this function is injective. We need to decide which n elements among the k elements of k can have free images, right? So that is what choosing n of these urns from the total available k urns. So that is the solution. So we have k choose n. Okay. Now, what is the next entry, right? So if the function is surjective instead of injective, then what can we say? So which means that each box or each urn can get at most one ball, right, inside. I mean, at least one ball, right? So, yeah, because we were looking at most one ball in the previous case. Yeah, so you should have at least one ball because it is surjective. So since each box must have at least one, any balls and is identical to any other ball. So what we can say is that, okay, let us put one ball each to the k ends first, so that we are, and they are identical, right? So I can just distribute them, and then now once I do this, then my question is now reduced to a previously solved question, right? Like, see, I have made sure that it is going to be surjective by selecting one ball for each of the ends, right? So every box must have at least one, so I put one in each of them. Now the remaining, whichever way I am going to distribute, the function has already become surjective, right? So how many ways I can do this? That is the different ways I can do this. That is going to be the number, because this one is a precondition that I need to fill up each of the ends at least one with at least one ball, right? So therefore, once you take away, right? So k balls are now used to fill up each of the k bins, right? So you have n minus k remaining balls, and that can be distributed, without any restriction, and distributing without restriction. That is basically something that we already did, right, in case 4, that we want n minus k element multi-sets from a k element set, right? So we have n minus k balls are there, and then you are going to put it into n minus a to k of these things, and then that is basically choosing the urns, right? So basically choosing an n minus k element multi-set from the available k from the k of the urns. This is precisely what we did in case 4, right? Case 4 was precisely doing this, right? That you had identical balls and boxes are labeled, and then how many ways you can do this. And precisely that is the way to do it. And in this case, it happens to be distribution of n minus k, because we have already used k to fill up the boxes with one ball each, right? So that is now k plus n minus k minus 1, choose n minus k, right? Because we want to, yeah, we start with k element set, and then we want to make n minus k element multi-sets. And what is this value, which is n minus 1, right, on the top, and then choose n minus k will become also k minus 1 when you take the complement. So therefore you get n minus 1, choose k minus 1. So another way to look at the same is, once you see that it is n minus 1 to k minus 1, we get this idea. So that so imagine you have these urns, right? All the boxes. The urns are as kids, okay, and the balls as ledus, right? We already solved this question, right? Ledus and kids. So we want to distribute the ledus to the kids so that everybody is happy, right? Everybody gets at least one, and because that's what we want when we want surjections, right? So basically the ledus has to be distributed to the kids who are the urns. So how many ways we can do this? We did this already, but let us review that. So we have placed the ledus in a line, right? We have this ledus in a line, and then we let the kids go from the beginning and then pick some ledus and then stop and then continue with the next person. So the first child always starts at the in its beginning position. So therefore, you need to decide among the remaining how many. So there were n ledus. So therefore, n minus 1 positions, right? Gaps. We have to decide where each of the remaining kids, right? The first kid already started, is going to start, right? So the remaining k minus 1 kids are going to start. So that is the way to choose k minus 1 positions, right, from the n minus 1 available gaps. So that is n minus 1 choose k minus 1. So this is another way to look at the same question. So we have filled the first two rows. Now the remaining two, right? So there are 6 is done, 6 more to go. Okay. So what is the next entry? So the seventh entry is that you have what is the question? You have labeled balls, right? Colored balls, and you have identical boxes. Okay. So since the boxes are identical, so if you look at the function going from n to k, so this function is captured fully by the non-empty pre-images of the elements of k, right? So you take the elements of k and then look at the non-empty pre-images, right? Like some of them may not be mapped to anything, right? Because the function is arbitrary. But if you take all the pre-images of the elements, you are going to get the set n. But the set n is now, if you collect them with respect to its image, what we are going to get is basically a partition of n, right? So this basically defines a partition of the set n, and the number of blocks is at most k because we are only having at most k boxes or k bins. What we are going to see is that you have you are looking at different ways of partitioning the set n into k at most k blocks, right? So that is the summation l equal to 1 to k s of n comma l, right? So that is s of n comma 1 plus s of n comma 2 plus etc. s of n comma k. So we get the seventh entry. So what is the next entry? Which is f is injective, right? So we have distinguishable balls and identical boxes and the injective function. So now see, if the number of we are looking at injective functions. If the number of balls are more than the number of boxes, there is no way to find an injective function, right? The cardinality of n is greater. So therefore, we have only these functions, injective functions, if the cardinality is cardinality of n is less than or equal to the cardinality of k, right? And how many are there, right? So if there is only one way because the boxes are all identical, right? Now you are going to partition the board so that each box has less than or equal to 1, right? So if you are going to put less than or equal to 1, then to the boxes, then there is only one way to do that, right? So you just put the balls to the boxes. That is it, right? So you just distribute them and then that is it. Because the balls are unlabeled, there is no other way to distinguish. So the answer is that it is 1 if n is less than or equal to k, and is 0 if n is greater than k. Okay. The ninth entry is that if f is surjective, right? So if f is surjective, then we observe that f inverse a is non-empty for all a in k. So thus the partition has exactly k blocks, right? Because each of the element has a pre-image, and there are k elements in k. So therefore there is exactly k blocks. Each pre-image defines a block, right? That we saw earlier. So therefore there is exactly s of n comma k, right? That is by definition that we have done. The number of surjective functions from from an element set to a k element set. So this defines this counts the number of surjections when the boxes are identical. Okay. Now what happens if the elements of n are indistinguishable, right? And the elements of k are also indistinguishable. This means that all the balls are identical, all the boxes are identical. So how do you count in this case? so since k, right, is the urns are unlabeled, we can partition n into like at most k blocks. But now the elements of n are basically identical, right? So it doesn't matter what are the elements because they are all identical, but it matters how many are there, right? So therefore, basically, it is partitioning the cardinality, right? The number of elements to to blocks. So that is basically integer partition. So number of ways of partitioning it, but then you can have at most k blocks because the function is arbitrary, and therefore, as in the previous case, we have summation p of n comma l, where l ranges from 1 to k, where p of nl is the number of ways of partitioning n to exactly l blocks, right? So integer partition. And what is the 11th question? Well, 11 is as we said in the case of 8, right? When the boxes are unlabeled, there is precisely one way to do it when n is less than or equal to k, and 0 ways if n is greater than k. The same thing holds here because again, it doesn't matter whether the balls are labeled or unlabeled, right? Even they are unlabeled, there is precisely one way to do it. And if n is less than or equal to k, and otherwise, no way to find an injection. And the final question, question number 12, is again similar to 9, but now integer partitioning to exactly k blocks because the function is a surjection. So we have p of n comma k. So we have the full table here now, right? So we have the balls which are distinguishable or indistinguishable, the boxes which are distinguishable or labeled. Then you have any function, right? Which means that unrestricted distribution. You have at most one per box which is injective functions. You have at least one per box which is surjective function. Right? So these are the 12 cases, and we have filled up all the entries. And each of these we have done in our previous classes. So I think that is basically like collecting so many different counting questions into the same framework, right? Of just distributing balls to bins, which is a nice way to look at this. I think. So that is the reason we looked at it, and a couple of homework questions. So one question is to count the number of compositions of an integer, let's say n strictly greater than 1, having an even number of even parts. Okay. Then the second question is give a combinatorial proof why distributing n identical votes to k labeled boxes is the same as basically the number of uh, distributions of k minus 1 identical balls to n plus 1 labeled boxes. Okay. So distributing n identical balls to k labeled boxes and distributing k minus 1 identical balls to n plus 1 labeled boxes apparently is the same, right? Like I mean the same in that, like they have, there is a bijection between them, they count the same number, or yeah, so the cardinalities are the same, which is kind of interesting to see, right? Like why should they be the same, right? So can you find a combinatorial proof? Of course, if you want to give an algebraic proof, I think it's very easy, there is nothing there. But we need a combinatorial proof why they are identical. Okay, so that is it. So we we have completed the homeworks parts for this question, and then let us see in the next class.